Welcome. This is lecture 41. In this we look at this Hilbert-Samuel polynomial and we look at its degree and prove some elementary results about it, which we will need in the proof of the main theorem. So recall Rm Noetherian local M finitely generated, I an M primary ideal, okay. Let me remind you, M primary is equivalent to saying that the radical is M because it is a maximal ideal. Okay. Then there exists a polynomial with rational coefficients such that the polynomial gives the value of the length of this module for all n greater than sufficiently large. Okay. And this is length as an R module. Because of this property, this module has finite length. The way we proved this was to look at the associated graded ring for associated graded module for M over the associated graded ring of R. In fact, the polynomial ring which surjects onto the associated graded ring. And there we proved that the individual graded pieces, the lengths vary by a linear combination of those binomial looking polynomials. And this is a sum of those things, and therefore this will also have that property. But we do not need that information for now. Okay, so here is the main, here is a proposition that we would need for later. So Rm I as above. Okay, let 0 to M prime to M double prime to M, sorry, M to M double, M prime to M double prime to 0 be an exact sequence of finitely generated R modules. Okay. Then we have three polynomials, the Hilbert-Samuel polynomial for each one of them. P I M prime plus P I M double prime. So this is a so this is the length of this P I M prime is this modulo I to the n plus 1m. It's eventually the value. This is the length of I this module. The second polynomial gives the length of this module times the power of modulo appropriate power of the ideal. One would so that would be a potential candidate for the corresponding object for this, but okay, so this is, but it's not exactly this. There is some extra term which is also going to be a polynomial because these two are polynomials, where degree of R is less than the degree of PIM, okay, and R has a leading, R has a positive leading coefficient. Okay, so this is the proposition. Okay, so how it behaves in a short exact sequence. So now proof is an application of Artem-Rees lemma. Okay. So this is not exactly equal. There will be some remainder term, but the remainder term. So what does this mean? Remainder term grows. Is a polynomial, of course, because the difference of a polynomial. It is it grows as in grows. That's what the positive leading coefficient means. And it grows much slower than than m mod in plus 1m because the degree is smaller. Okay, but So this is, so let's prove this. Proof is a okay, so proof is just an application of Artem's lemma after we set something up. Okay, so we are given 0 to m prime to m double prime to 0. Okay, so this gives zero to m prime mod m prime intersect I n m. So we are going modulo I n in all of these modules. M mod I n m to m double prime mod I n m double prime to 0. Okay, so let's just discuss this just briefly. So we want to go modulo I n times these modules respectively. Okay, so here we kill that. It's so that, and then we are killing. So m to m double prime amounts to killing m prime. Okay, so if you additionally kill I to the n times m here, it will also kill I to the n times m double prime, because the image of I to the n times m inside here is I to the n double prime, and we get a surjective map. Okay, so that explains the surjective map. So now let's look at what happens, what's the kernel of this. So what, if you think about m, okay, if you think about m mapping to this, so note, so let's think about m mapping to this and that mapping to this. Okay, so in this composite, what goes to 0? Well, first m prime goes to 0 and then I to the n m goes to 0. So the kernel of this map, m to this, is exactly m prime plus I to the n m. Okay, so if you think about, okay, so therefore the kernel for this map would be, okay, so if you look at this map, what I just said is, if you look at this map, okay, kernel is m prime plus I n m. Okay, therefore kernel of this map here, therefore kernel of m mod I n m surjecting onto m double prime mod I n plus I n m prime, okay, this is, okay, this is just I n m plus m prime mod I n m, which is same thing as m prime over m prime intersect I n m. Okay, so that's what we wrote here. Okay, so that gives us this term. Okay, so it is this short exact sequence that we want to consider. Okay, so now let's so we are given a filtration of m by powers of I, and here also by powers of I. Here we get a different filtration. So this is the context in which we will need to apply Artem's lemma. Write m prime n as m prime intersect I n m. Okay. Okay. So what does this now tell us? It tells us that the length of this equals length of this minus the length of this equals this length. Okay. So therefore we get p I m n minus p I m double prime n equals the length over R of m prime mod m prime n for all sufficiently large n. Okay. So remember, these give the length only for sufficiently large n. So the However, this is the difference of the lengths, not the difference of the polynomials. Okay, so this is, we get this. Okay, so the conclusion is that this function, so this function n mapping to this length, okay, this function is given by a polynomial, therefore is given by a polynomial for large n. Okay. So exactly, I mean, sort of like a Hilbert function itself. Okay. So now, by Artem-Rees lemma, okay, so by the Artem-Rees lemma, okay, what does Artem? So it says that, so Artem-Rees lemma says that if you look at the filtration, this is so Artem-Rees lemma, the filtration given by m prime n, okay, the m prime intersect the power of filtration of m is I stable. Okay. That is, there exists some n0 such that for all n greater than or equal to n0, I times m prime n plus m prime n equals m prime n plus 1. Okay. So this, in other words, that module m, the module m star that we constructed for this m prime, okay, over the ring R star, it is finitely generated. Okay. So this is equivalent to that statement. Okay. So, so this is what, okay. Now let's, so in other words, okay, if you take some n prime plus some n, in other words, therefore, sorry, not in other words, therefore, okay, if we take I to some large power which is bigger than n0, okay, this n naught here, okay, times m prime, okay. This is of course inside m n0 plus n. That's the property of stable filtration. That first of all, there is this containment for every n, and for sufficiently large n, I times 1 nth piece is equal to the n plus 1th piece. Okay, so that's Artem-Rees lemma. Okay, so this is inside here, but repeatedly applying this, therefore for all n greater than or equal to 1, if you take this and repeatedly applying this, so there's a slight change in notation here. Please bear that in mind. Here it's all n greater than or equal to n0, but here I am taking that as a difference from n0. Okay, so this is same thing as I to the n times mn 0, that just repeatedly applying this result. Okay, and this is inside I to the n times m prime. Okay, so let's just look at this for a minute. We know that I times m prime is inside. Okay. So, so we get this relation. Now let's take lengths. This means that length of m prime mod I n0 plus n m prime. Okay, so we're killing a smaller submodule, so it will have a bigger length. This is greater than or equal to length of m mod m n0 plus n. That is just from this relation. okay, and these two are anyway equal, and this is greater than or equal to length of m prime mod in m prime. Okay, so this is okay, so we get this result. Okay. So now we know that these lengths for sufficiently large n are given by polynomials. Okay. Therefore, for all n sufficiently large, pi of m prime, okay, evaluated at n0 plus n. So this is, so let me just, so in order, I mean, so let's just go back to this, just a note, I mean, remember PIMN n is length of m modulo I to the n plus 1 m, but since we are arguing for all sufficiently large n, there, I mean, between these two terms there is an offset of 1, but that is okay. Okay, so this is, I mean, this is really, one has to put a plus 1 in this term here. I mean, this is equal to this expression with n0 plus n plus 1, but okay, that's fine. Okay, so this is greater than or equal to this length m, this middle thing m, sorry, what actually, sorry, these are all should have been m prime, not m, sorry, all of them should have been primes. Okay, and m prime, this also here, m prime, okay, m prime n0 plus n, okay, and this is greater than or equal to this thing again with an offset of 1, which is given by pi m prime of n for all sufficiently large n. Okay, so now we already proved that this is a polynomial function. M prime modulo m prime n going to this is a polynomial function. Okay, this says that they are polynomial function with the same degree and same leading coefficient, because otherwise, so this is a polynomial function. We proved that this is a polynomial. Okay. That's because polynomial, sorry, for large n. Okay, but that is enough. The behavior, asymptotic behavior, will be determined by its leading coefficient and degree, so they all have to be the same in these things. Okay, so which now proves that okay, so now what do we know? So this, okay, so now this implies that pi m prime, okay, minus, so define this, so this is the r that we had, the difference of these two polynomials is the r that we have, we would define okay, this define this to be the function, the polynomial r. So remember in the oh, sorry, maybe I should use maybe I should just use some q here, because when sorry, r was also the notation for the ring, although it's not ever used afterwards. Okay, so this is the polynomial q that we asserted exists. Okay, so this is a polynomial. Okay, it has degree, okay, less than or equal to the degree of PIM. Okay. And moreover, its leading coefficient has to be positive, because as n goes to infinity, this difference is positive. Okay. So remember, it is this difference. I mean, this q of n0 plus n minus 1 is this difference, and it is positive. Okay. Since q of n is non-negative for all sufficiently large n, that's from this relation. So okay, it is the difference of these two that we called q. Okay. Its leading coefficient must be positive. Okay. So this is the end of this proof. Okay. So we won't need the full detail of this proof for us to use, but we do need the fact, we do need to use it in the following way. Okay. Corollary, okay, with notation as in the proposition. Delta of m, which is the degree of that PIM, is greater than or equal to delta of m prime. M double prime, it is sort of easier to see because of the surjectivity. Okay. I mean, this length is always less than or equal to this length. So this degree of this polynomial for m double prime will always be less than or equal to the degree of PIM. It's the other one that required some this argument. Okay, this is. Okay. Why is that the case? Notice that. Okay, so note that proof. PIM minus PIM m prime minus PIM double prime has degree less than degree of PIM and has positive leading coefficient. Okay. In other words, if this sum here, let's write like this, if this sum here had a degree which is bigger than degree of this, then that thing, the degree of the difference would be the degree of this. Okay, so let's just write this. If degree of PIM degree of P, maybe let's just quickly observe this part. Degree of their sum is equal to the maximum of their individual degrees. Okay, that's because they both have, since they have positive leading coefficients. The leading terms can never cancel each other when you take the sum. Okay, so using this, so this side, and the difference has smaller degree. So therefore, the leading term of this and leading term of that, if this thing had strictly had positive degree, strictly bigger than the degree of PIM, then the difference will have degree equal to the degree of this. Okay, so therefore, if degree of PIM m prime plus PIM double prime is strictly bigger than the degree of PIM, the polynomial Q in the proposition will have degree will have degree greater than degree of greater than degree of PIM, which is a contradiction. Okay. So in other words, degree of PIM prime is less than or equal to degree of PIM, okay, because the other one is anyway smaller. The max of this is less than or equal to this. So this, okay. Another corollary is if x is a non-zero divisor, same notation as in the theorem, non-zero divisor on M, then delta of M mod xm is strictly smaller. Okay. And why is this? This is because, so consider proof. We have an exact sequence, okay, 0 to m multiplication by x and m mod xm to 0, and this is injective here because x is a non-zero divisor. Okay. So then we apply the proposition to this. It says the sum of these two is this plus some difference which is positive leading coefficient and smaller degree. Okay. So proposition gives so the outer two, which is degree of PIM plus degree of PIM mod xm, these are the outer two, equals just PIM plus PIM equals PIM plus some q, okay. Therefore, PIM mod xm is q, and proposition says that by proposition delta of m mod xm is degree of q, which is degree of PIM, which is what we wanted to prove. So if you have a non-zero divisor and you go modulo that, then delta strictly decreases. Okay, so we need one more observation about the relation between one relation among the number of the length of a system of parameters and delta. Okay, so which slightly so we need to see the proof. So we will do that first thing in the next lecture, and then we will prove. We will look at a little bit more about systems of parameters in Macaulay 2, and then we will prove the theorem.